How does a buck converter work in electrical engineering? Have you ever wondered how devices efficiently convert higher voltage levels to lower ones? Today, we will uncover the workings of a buck converter, a key player in electrical engineering. This device is a type of direct current to direct current power converter that steps down voltage while increasing current. You will often find it in power electronics, especially within power systems and renewable energy applications. The operation of a buck converter revolves around a switching element, typically a transistor, and an energy storage component known as an inductor. When the transistor switch is activated, the input voltage is applied across the inductor. This causes the current through the inductor to rise gradually, storing energy in its magnetic field. During this on phase, the inductor current increases, supplying energy to the load and charging an output capacitor that smooths out the voltage. Now, when the switch turns off, the inductor current cannot change instantly. Instead, it continues to flow, but now through a diode or a synchronous switch to the load. The inductor releases its stored energy, maintaining the current flow and preventing the output voltage from dropping suddenly. This off phase causes the voltage across the inductor to reverse polarity, effectively subtracting voltage from the input. This is why we call it a buck converter. The output voltage is controlled by adjusting the duty cycle of the switching signal. The duty cycle is the ratio of the time the switch is on to the total switching period. A higher duty cycle means the switch stays on longer, resulting in a higher average output voltage, but it will always be less than the input voltage. The combination of the output capacitor and inductor smooths out the output current and voltage, reducing ripple. More advanced designs may replace the diode with a second transistor, known as synchronous rectification. This change reduces losses associated with the diode's forward voltage drop, improving overall efficiency. Control circuits, often using feedback loops and pulse width modulation, help maintain a stable output voltage even when the load or input voltage changes. In the field of electrical engineering, buck converters play a vital role in power electronics by providing efficient voltage regulation. This is especially important in renewable energy systems, where converting variable direct current voltages from sources like solar panels into stable, usable voltages is essential. They achieve high efficiency, often exceeding 80 to 90%, which reduces heat dissipation and enhances system reliability. Key components of a buck converter include the inductor, which stores energy and smooths current, the switching transistor, which rapidly turns the input voltage on and off, the diode or synchronous switch, which provides a path for inductor current when the main switch is off, the output capacitor, which reduces voltage ripple, and the feedback control system, which ensures stable output voltage under varying conditions. Overall, the buck converter is a fundamental component in power electronics, efficiently converting higher direct current voltages to lower levels for various electrical engineering applications.